We're going to start this lesson with a quick review from geometry about special right triangles. Remember, in any right triangle, the hypotenuse is the side that is opposite the right angle. The other two sides of the triangle are called legs. Now, depending on the measure of these angles, we can know some things maybe about the relationship between the legs or between the legs and the hypotenuse. But just in general, we know that this is true for any right triangle that we work with from geometry. Now, when we're working with a 45, 45, 90 triangle, that's one of those special right triangles, we know some things about the two angles that are opposite the legs in this right triangle. We know that if this angle is 45 degrees, given we're in a right triangle, then this angle must also be 45 degrees. And so the sides opposite of those angles, since the angle measures are equal, the side measures equal one another as well. So if this side measures in, then the other leg in a 45, 45, 90 must also measure in. And it turns out that there is a direct relationship between the legs and the hypotenuse in a 45, 45, 90. And that is that we can take the measure of one or the other leg and multiply it by the square roots of 2, and we're guaranteed that that will be the length of the hypotenuse in a 45, 45, 90. Now, the reason that a 45, 45, 90 right triangle is so important is because it leads us to some exact values on our trig ratios that we also remember from geometry and probably algebra 2. So these 45, 45, 90 triangles are important to us in trigonometry. But just really quickly as a review, if we know that we are in a 45, 45, 90, if they either show us that we are or we can determine that we are, in this case both legs are the same measure, then we can solve for some unknowns. For instance, if I want to know the measure of the hypotenuse in this 45, 45, 90, I know that the hypotenuse is the square roots of 2 times the measure of one of the legs. So it's easy for us to find missing side lengths in a 45, 45, 90. Here we know that the hypotenuse is 2 times the square roots of 6, which remember is just a leg times the square roots of 3. So if we were actually to try to solve for x, we would use this relationship right here, and that's going to allow us to solve for x. We would divide both sides by the square roots of 3, and x would have to be this value. Now we can rationalize the denominator and all that kind of stuff, but that's just algebra work. But we can solve for unknown values or side measures using our 45, 45, 90 relationship. What we're going to do with them in trigonometry is we are going to come up with our exact values. And for us, when we're in the plane, remember that we always put those angle measures in standard position. So we would say that this was our angle measure, theta. And in this case, I'm going to say theta is 45 degrees. And here is my right triangle. So I know that this measure is 45 degrees. And let's say that my radius is 1. Let's say the distance from the origin to this point in the plane is the radius of a circle. We had talked about that before. And so let's say our radius is 1. And if that's the case, that means our hypotenuse is 1. And since we know that our legs, right, are, let's say this, square roots of 2 times a leg, if we solve that for L, we know that L therefore has to be our hypotenuse divided by the square roots of 2. That's me just taking this and using algebra on it. And now if I'm in a right triangle that has a hypotenuse of 1, then what I'm going to do is just replace h with 1. And in here, the denominator of this fraction has been rationalized. Remember, we do that by multiplying by a well-chosen 1. 1 times the square roots of 2 is the square roots of 2. Square roots of 2 times the square roots of 2 is the square roots of 4, which is 2. So that's why we can say when we know our hypotenuse is 1, we know that the length of each leg is the square root of 2 over 2. And that is what we call an exact value for a theta measure in trigonometry. Now we have more theta measures that we get exact values on. 45 degrees is just one of them. The other two that we get, we're going to do the same thing in the next lesson. We'll see exact values for 30 degrees and we'll look at exact values for 60 degrees. So exact values are pretty important when it comes to our trigonometry work. So let's see how we can tie what we know is happening from geometry in a 45, 45, 90 triangle, how we can tie it into what we need to use in trigonometry. So let's do just a little bit of a trig review. Let's go back and let's talk about how you were taught to find the ratios for sine, cosine, and tangent. You were probably taught something along these lines, maybe some old hippie or something like that. But we know that the sine of any angle measure, it doesn't matter what theta measures, the sine of theta in any right triangle can always be found by taking the length of the opposite side, and that's opposite to theta. This is adjacent to theta. Here is the hypotenuse because it's across from the right angle. So we take the length of the opposite side and put that over the length of the hypotenuse. And that ratio is what we call the sine of the angle measure theta. We know that the cosine of theta is the length of the adjacent leg divided by the length of the hypotenuse. And that's where we get SOHCA. And so adjacent over hypotenuse, that's ratio of lengths of two sides of a right triangle, is going to be the cosine of our theta measure. And tangent is the opposite side divided by the adjacent side. So that's where you get the TOA from in SOHCA-TOA. So opposite side length divided by adjacent side length is equivalent to the tangent of our angle measure, which here is called theta. We know that there are reciprocal relationships with sine, cosine, and tangent as well. So there are 6 trig functions that we're responsible for knowing. We just learned these and these relationships through SOHCA-TOA, and then we take the reciprocal relationships and use algebra to come up with the ratios that are secant, cosecant, and cotangent. So if 1 over cosine of theta is secant of theta, it has to be true then that 1 over adjacent divided by hypotenuse must therefore be the secant of theta. And we're going to use that compound fraction idea. We take the fraction on the bottom, flip it, and multiply straight across. So we're actually going to come up with the hypotenuse over the adjacent side is going to be equivalent to secant of theta. And cosecant, which is 1 over sine, so that's 1 over opposite over hypotenuse, would therefore algebraically be equivalent to hypotenuse over the opposite side. And 1 over tangent, which is cotangent, tangent is opposite over adjacent, so 1 over opposite over adjacent algebraically becomes adjacent over opposite. So we have all 3 ratios based on the reciprocal relationship between secant, 1 over cosine, cosecant, 1 over sine, cotangent, 1 over tan. So there's 6 trig functions, 6 trig relationships that we're going to be responsible for. These are the 3 biggies. We work with these a lot, but we will see these as well in our trig work. Remember that there is this relationship that is also defined to be the tangent of theta as well. The reason that the tangent of theta is the opposite side over the adjacent side is because it is the sine ratio, remember, which is opposite over hypotenuse, divided by the cosine ratio, which is adjacent over hypotenuse. And algebraically, we take that one on bottom and we flip it, and multiply straight across, and therefore our h's will go away, and that's why tangent is opposite over adjacent. So sometimes it's helpful to use this relationship as well. We might know the sine, we might know the cosine, and therefore we can figure out what the tangent of some angle measure of theta is. So now let's take the opportunity to tie in together what we did with our 45, 45, 90 right triangle and what we're going to do in the plane and our trig units. So here I have, I'm showing part of a circle. I have some special angle measures that are listed here. Remember, this is equal to 30 degrees, pi over 6 radians. Pi over 4 radians is equal to 45 degrees. That's the one we're going to work with today. Pi over 3 radians is equal to 60 degrees. And of course, we remember pi over 2 radians is equal to 90 degrees. So I'm going to just drop this altitude right here in the plane from this point on the surface of that circle. I know that this hypotenuse, this measure, is 1. And this angle measure is given to me right here. It is pi over 4, or equivalent to 45 degrees. Everything that's true about a 45, 45, 90 is true here because this is an equivalent measure. It's just done with a different measuring stick, right? It's just done measuring radians instead of measuring degrees. But what I know about 45, 45, 90s is definitely true. So what we said is that we know if our radius is 1, we know that this side length is square roots of 2 over 2, and we know that this side length is square roots of 2 over 2. So we determined that. Let's go back up here and I'll prove that to you. Remember, we determined that right here. That's based on our hypotenuse being 1 and on the fact that we are in a 45, 45, 90 triangle. So now we're going to sit that in the plane, this triangle, with our radian angle measures, and we're going to determine that this is the opposite side of our angle and this is the adjacent side of our angle. So if we wanted to find all of our trig ratios, we could start out with the sine of pi over 4. Remember, that's equivalent to 45 degrees, but we're going to use radians. So the sine of pi over 4, which is the opposite side over the hypotenuse, has to be the square roots of 2 over 2 all over 1. And our hypotenuse is 1, so I won't draw a line and write over 1, but recognize that it's there. So we know the sine of pi over 4 is root 2 over 2. We know the cosine of pi over 4 is adjacent over hypotenuse. So the cosine is the same. It's the square root of 2 over 2. We know that the tangent of pi over 4 is opposite, here's opposite, over adjacent. Well, they're equal. So the square root of 2 over 2 divided by the square root of 2 over 2 is 1. So the tangent of pi over 4 is 1. Now let's continue with the cosine, or the reciprocal sign. That's cosecant of pi over 4. And remember, it is, if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. So let's do a little algebra here. That's going to be 1 over the square roots of 2 over 2, and we can flip that bottom one and multiply straight across, so that would be 2 over the square roots of 2. And for some reason in math they don't like radicals in the denominator, so let's rationalize that denominator. So we're going to have 2 times the square root of 2, I'm just multiplying straight across here, over square root of 2 times square root of 2 is square root of 4, or that's just 2. Those have a value of 1, so the cosecant of pi over 4 is just the square root of 2. Now let's talk about the secant